see tomorrow. So this will be a rather, I guess, simple observation, but really the hope is that this might well, give rise to more interesting, involved future work. So let us look at a very simple example. So here we have two scalar stable systems. So you can think of this curve as, for example, a spring, and of the other curve as, for example, a stable damper. Now, of course, you would say, okay, these are clearly different, but maybe they came from the same system, and the damper is just here shown using a very unfortunate set of coordinates. So maybe there's a way to transform this damper to the spring. So you might ask, is there a homeomorphism, let's say phi, such that we can indeed transform the damper into the spring? Now, if you plug this into the equations, you get that this following expression must hold. Since these homeomorphisms in the scalar case are necessarily monotone, it's not too hard to convince yourself that this cannot be true. So the intuition is correct. So these systems, regardless of the coordinates you pick, are somehow inherently, they are different, right? They are structurally different, and in this case, because they have, right, the maps have a different orientation. So this is sort of what we'll look at today, at these kind of structural either differences or equivalences. So in fact, we'll look at discrete systems, which in this case will be just deterministic and parameterized by some map F, right? And usually in the control context, you can think of this map F of X as some closed loop map. So maybe it was depending on some input U, as we saw before, but then if you assume that this U is actually given by some state feedback, you can think of this map, right? You can plug it in and you can think of the map just depending on the state X. Now, these kind of maps, they usually show up in optimal control problems because effectively, although you optimize over some inputs, you're changing usually these closed loop systems. So what we will see is that if you look at a particular class of, in this case, of cost functions, then the resulting closed loop systems, they will have some structural similarities. This is essentially the main message of today. So to formalize this type of equivalence, we will talk about topological equivalence. Intuitively, this means that these phase portraits, they will be homeomorphic and they have to agree on time, which relates to stability. So you can think of this in the continuous time case, but there it can be quite hard to deal with because you need to work with the flows, with the solutions if you want, which can be hard. But in the discrete time case, you can directly work with the time one maps, in this case, for example, F and G, and you need to look for such a map, phi, which satisfies this relation. So to define it a bit more formally again, we say that two, in this case, you can just think of dynamical systems, but two endomorphisms, F and G, are topologically equivalent, which coincides with them being conjugates if the following diagram commutes. So this just means that there is a very general and discontinuous change of coordinates. So there should be some kind of, in this case, homeomorphism, which relates their orbit. Okay. So to exemplify this in the most simple setting, we can look at just scalar linear maps. So say F is A times X and G is say B times Y. So in this case, it turns out that the different classes you can have are just 7 classes. You have these 4 intervals at these 3 points. So for example, A could live in this class 5 and B in this class 7. And in fact, you can work out explicitly what the corresponding homeomorphism, if they are members of the same class, what this homeomorphism is. So let's say you have F is 2 times X and G is 8 times Y, then clearly they are different, but structurally they are the same, right? They preserve, both of them preserve orientation and they're unstable. And you can see that the homeomorphism in this case, the map itself might be analytic over R, while the inverse is just continuous, right? So really assuming anything more than continuity is already a bit too much. But the point is of this whole classification is that you can look at finite classes of system instead of, in case of the linear systems, instead of, for example, using similarity transformations, which would yield still like a whole continuum of systems, which is not so much of a step forward. Now, in some sense, this looking at these finite classes was also the initial motivation by, for example, Poincaré or Birkhoff, and this showed up in many of the famous theorems like the Hartmann-Grobman theorem. And of course, this is the key tool in bifurcation theory as well. And in fact, one of the founding fathers, I should say, of perhaps the Dutch school of control theory, Jan Willem, said that these kind of tools, also in the control context, he thought they were so important that there's no doubt that they will become standard amongst all the practitioners. Now, I did control theory even in the Netherlands, and I can tell you this is not the case at all. It did not show up anywhere. So is this really true? So this might relate to the comment made in a similar time by, I would say again, well, quite legends in the field, and they stated that the original work, although very beautiful, they focused on global classifications of systems, and again, that case of nonlinear systems, and this is just rather hard. So people looked at classifications around equilibrium or fixed points to make it a bit more tangible. So yeah, what's the point now? Is it still a nice field? Should we continue with this? Well, I hope that today I give you a very simple example where we see that indeed still this topological classification is doable and gives us some really, I would say, nice insights. So we look at a very simple setting today, just at linear maps. So this F is just a matrix F, and we want to focus on if you want, on the automorphic part, but just to keep it even more simple, we just assume that F is invertible. So you can think of these kind of trajectories. So since, of course, if we assume F to be invertible, then we will look at the general linear group, and this is just to fix notation essentially. So you, of course, you can decompose the general linear group, the real one, in its two path-connected components, which we denote by GLN plus and GLN minus, which corresponds to the sign of the determinant of the matrices in these parts. Now, of course, this group is dense, so you cannot really think of it like this, but intuitively, it helps to think of it as two separate sort of parts in which you can have these kind of paths cover. Okay, so we will also add some more structure. So we're not just interested in invertible maps, but also in stable maps, because usually these things correspond to a control problem, and in the end you end up with a stable closed loop system. So we need some form of stability for these maps. So we will look at the set of what some people would call asymptotically stable matrices, which are just, again, matrices where the spectral radius is smaller than 1. And then the point is that if you have such a matrix, then this limit, regardless of your choice of x, will go to 0. Okay, so this is our sort of starting point. Given the fact that we have a map, which is where the matrix which parameterizes this map is and invertible and stable, we can appeal to a rather nice characterization of topological equivalence. So I'm not sure if this is actually a result by Robinson or this is one of the first books where it was stated, but anyway, I took the theorem from that book. And this theorem states that if you have two, what we have are two invertible linear maps, which are both stable, and they belong to the same path-connected component of the general linear group, then they are then the systems they parameterize are topologically equivalent. So visually, you can think of it like this, right? The set of asymptotically stable matrices might not fully coincide, of course, with the general linear group. But if you do have two matrices F and G, which are both stable and in the same path-connected components, then indeed these the corresponding systems, they are topologically equivalent. So this is a very nice characterization, and it's very, I would say, practically useful. Okay, now we will apply precisely this theorem in the context of linear quadratic optimal control, which I guess we will see more of this week. So we look at the most simple case, so it's just a deterministic discrete time problem where we have this infinite horizon. So what we do is we call this the stage cost. Some people call this the stage cost, which is in this case quadratic, hence the name. And we have linear dynamics, which we sometimes use this sigma to describe sort of the forced time one map. Now this is the most general form, but if you look at the literature, any book, I would say 99% of the time people remove this S matrix and just look at what they call this sort of diagonal form. Okay, and if you do that, then there's lots of theory which states that if your under certain conditions on your A and B matrices on your system, and these cost matrices, the solution is explicitly given by this linear state feedback and is parameterized by what they call a Riccati equation. In fact, the resulting closed loop map is asymptotically stable. Now, if you go to any, I would say, let's say, robotics department, people will talk all day long about tuning these matrices Q and R to get desired behavior. But whatever this means is up to them, but they will tell you that this is very important and it means a lot. Now we will see actually today what this means. So what can you really do? For example, could you go, if you have a stable spring, by changing these matrices, can you go to this stable damper, right? It's still a stable system, so maybe you're still happy, but can you actually achieve this by just changing your optimal control cost? Okay, this is the most basic diagonal setting, but we can also look at a more general setting if you want. So where these matrices S are non-zero, then we can apply some transformations. Well, so you change the input, you change this Q matrix, and you change your drift term A, and you still end up with this diagonal form. So it's theoretically not that much more complicated. The only thing we need to assume is that the rank of this Q prime is the same as the rank of Q to be able to use the previous conditions on your system. Okay, so given this information, we can characterize sort of the set of cost matrices we are interested in, or we look at. So what we can do is we assume that this A and B pair is stabilizable, which just means that there exists a solution, if you want. And then we will look at the cost matrices in this set. So this, again, this just, you do not have to worry too much about all of this. It just means that there exists a solution to the optimal control problem. So we will look at these cost matrices and we're interested in what happens when you change them. So to what extent can you indeed go, for example, from the spring to a damper, and when? So that's interesting. I already said that usually people completely ignore this S matrix. And in fact, one of the few results I could find where they used it was in this setting where they could stabilize this, I would say, rather impressive mechanical object just locally using these linear tools. And they stated that they used this S matrix to penalize sort of subsequent errors in the input, which removes some oscillations. But this is, of course, still somewhat, they motivated it quite clearly, but still somewhat of, I would say, heuristic motivation of why you should do that. So can we say something more? So to that end, we will slightly alter the set of these cost matrices and we make it orientation dependent. So we assume that our matrix A is invertible. It's a member of one of these path-connected components, and we enforce these cost matrices to be such that this A prime, which is the transformed version, is a member of the same path-connected component. And then we can state the following. So we let A be such a matrix. Then we pick any triple from this set, which gives rise to some closed loop map. And if we pick any other triple from the set, then these two systems will be topologically equivalent. And actually, this is very easy to show because it turns out that all of these resulting closed loop systems are of this form where this lambda matrix is a member of GLM plus, which means that this membership is how do you say it? It's invariant under applying this lambda inverse. So it's a sort of straightforward result, but the implication is the following. In practice, everybody uses just these Q and R matrices and is talking about tuning all day long, but it means this result that if you do not have an S, then all of the matrices in this set, they give rise to topologically equivalent systems. So when people talk about tuning all day long, actually they're not structurally tuning, they just tune perhaps some rates or some, well, yeah, that's what they're tuning, some decay rates or something else, but they're not structurally tuning. So there's no way that if you change these matrices, you can go from a spring to a damper. So it's really structurally stable in some sense. But if you do introduce an S, then it's possible. So then you can, formally speaking, you can introduce a bifurcation in your closed loop system. Now, this result has also some implications, for example, in the field of what they call inverse optimal control, where they want to find, given some system, is there a an optimal control problem which generates this system. Well, it turns out that if you have any linear feedback, you can sort of write the criticals like this, and then there's always some optimal control problem for which this feedback was optimal. But here you see that you do have these cross terms in the cost. So then given this result, you see that sort of if you have an inverse optimal control problem where you do not allow for cross terms, you neglect the whole class of systems. So this is also a new insight in that sense. Now, one of the, I would say, this is of course, this result is fully tailored to the LQR case, because here we have an explicit expression for the closed-loop system, and it's not so clear if we can actually do this in a more involved, interesting setting. But we can look at also at this problem using the maximum principle. So to that end, we have to define what's the symplectic group. And it turns out that the LQR problem we just discussed gives rise to this Hamiltonian matrix. And you can argue if you should call this a Hamiltonian or not, but that's indeed traditional terminology. What we can do is, let me say, okay, we parameterize these cost matrices, let's say by some gamma, which means that this M is parameterized by gamma, and A prime and Q prime, and these things are all functions of gamma. And we can state the following. So we pick some curve, in this case it's a curve, in the set of feasible matrices, if you want. And we look at the start and the end point, just for simplicity. And then it turns out that if you can find, or if actually this M, which is also a function of gamma, is then a continuous path in a symplectic group, then indeed these two systems are topologically equivalent. So visually, you will have, in this case, it will be 2, but if you have, by changing this gamma or a gamma, you have curves in the symplectic group, which are continuous curves in the symplectic group, then the closed loop systems they generate, they will be topologically equivalent. So this is the same result. It's sort of a corollary to the previous result, but it's a different point of view. And this result might allow, in some sense, to be generalized to more involved problems, to different Hamiltonians, because in some sense this relates to these, if you want these Hamiltonians to be homotopy equivalent using this gamma. So this could perhaps be generalized. Okay, so this was the key result. Now we can visualize what happens. So if you have some LQR problem and you have, let's say, some S matrix. So here the determinant of A is 1. So then as long as you pick this epsilon sufficiently small, then this A prime will have the same orientation. So what we see is if this epsilon is small, you do have, well, you start from a counterclockwise spiral. If you start to increase it, it remains such a spiral, but once you increase it too far, indeed, this behavior breaks down. So this is just a visualization of what we saw before. Indeed, S allows for introducing these bifurcations. Now there's a different field where you can apply these same ideas as well, and that's actually in the continuous time case. Let's say you have a simple linear differential equation. If you would sample this thing, it would give rise to this discrete or this time one map, which is always orientation preserving. And actually the same holds for locally for Poincare maps as well. So this could be a wildly nonlinear system where you, for example, want to stabilize this red orbit. And then what people do is they look locally around this X star, they look at this then will be also a linear discrete map, how to stabilize this point. And in fact, again, this thing is also orientation preserving. Now it would be interesting to see what happens in the controlled case. So this stabilization of these orbits shows up in many fields, so in biology and robotics, everywhere. And now what they do is they just stabilize it using totally random tools, and they just hope for the best. Because if you stabilize it on this plane sigma, you have no clue what will happen. Usually you don't really know what will happen here. So we can do, again, a very simple example. So we can look at this affine system, which will have a fixed point for R is 1 and U is 0. But it's an unstable orbit. So the orbit is in this case the circle, but it's unstable. I will not go through all of the derivation, but we will assume that we let the input to be constant from impact to impact. So for one rotation, then you can derive the full Poincare map, you can linearize it, and you end up with some linear system you want to stabilize. Now you could use this LQR tools, which we saw before, or you could use something else, right? You can use, there are many different control tools, you can do whatever you want. So we will design some LQR gain for this linear system. At the same time, we find some k tilde, which is numerically will be very close to the LQR gain, but it's a different gain. Now, what we see is that this LQR gain, as we proved before, it should, since this locally, this Poincare map was orientation preserving, this LQR, adding this LQR feedback also preserves the orientation. So if you have such a periodic orbit, orientation is preserved. While for this other feedback, it's not the case. So this is in some sense just a periodic version of what we saw in the very beginning. So this, you can think of this as the periodic damper, and this is the periodic spring behavior. But since people, for example, in robotics at the moment, they just apply arbitrary control tools, maybe it's much more beneficial. This motivates why you might want to use LQR, because it's a more general motion, and these kind of things could be generated. They could come from continuous time systems, while this is not possible. So this is some motivation again to locally use, for example, LQR. Now, it turns out that all of these results, it was just for the most simple setting, but you can, all of this holds for the generalizations of this problem. So you can add, you can also maximize over, if you want worst case models, you can look at dynamic games, robust control, exponential costs, and still this holds. So it's a very, in some sense, general result for this whole family of linear quadratic optimal control problems. So in some sense, there is not so much difference, right? In some sense, all of them result in, topologically speaking, the same behavior. So the whole fuss about all of the differences you get is it's not really, yeah, it's not really true. So with that, I would like to end, and I think if you want to read more, I can definitely recommend this first paper where I think they started this whole investigation. So thanks a lot.